In this lesson, we're looking at reviewing function notation, but more importantly, the templates that we use for sketching and modeling. The translation-based templates, that is, we're looking at a scenario where we've got y is equal to a f of x take h plus k. Now, we'll talk about that in a second, but basically we're looking at scenarios where we've got a base function with an associated shape, and we're translating it left, right, up, down, and dilating it vertically with that factor of a. So far, we've looked at general functions, parabolas, hyperbolas, cubics, and inverse parabolas. So you should at least have an idea of those shapes and how it applies. So we'll reintroduce those, remind you of what they look like. We'll look at sketching functions, and then we'll look at modeling, so working back from a graph. Okay, we'll start by quickly going through function notation. Now, the whole idea with function notation is that it's a bit of a shortcut, so it saves us from having to write things out. Let's say we've got y is equal to 2x take 3 squared plus 1. So that's our equation. And we want to work out some different values, so we want to do some substitution. In the old way of doing this, we would have said that, okay, let x equal 3, for example, and then we would say that y is equal to 3 take 3 squared plus 1, and then it's 2 times 0, so we end up with 1. We've got 3, 1 is a ordered pair of coordinate that fits with this function. Now, with function notation, we can short that. So instead of looking at y, we'll say that it's going to be f of x. That means that we've got a function where the variable is x. So we'll say that f of x is equal to 2x take 3 squared plus 1. And instead of having to say let x be, we can go straight away f of 3 is equal to, and so that's saying that we're going to sub 3 in, and we're trying to work out what the y value is. 3 take 3 squared plus 1, which is equal to 1. And so that means x is 3, y is 1, and we've got our coordinate 3, 1. So it's an alternative way to do it. It will be used a lot throughout the course, so it's important that you understand function notation. It will pop up all the time, so we just want to make sure we understand what's going on. And also utilizing it allows us to save time and space. Just a really quick example. We can see here that it tells us, so we've got a function, f of x is equal to x squared take 3. So that's our function, y is equal to x squared take 3. And we're looking at f of negative 2. So f of negative 2 will be negative 2 squared take 3. 4 take 3 is 1. So there we have it. The y value when x is negative 2 is 1. For part b, we've got f of a, so that's saying that we're going to sub a into the equation. So we've got a squared take 3. Now there's no simplification for that, so there it is. When x is equal to a, then y is equal to a squared take 3. When we look at f of 2a, we're subbing in 2a into the equation, so we've got 2a squared take 3. Following our index laws, power to all, we get 2 squared, which is 4, so we've got 4a squared take 3. So when x is equal to 2a, y is equal to 4a squared take 3. And then finally, we've got f of a plus 1, and so that means we've got a plus 1 all squared take 3. Now, because we're nice and efficient with our perfect squares, we know that's going to be a squared plus 2a plus 1. Remembering, if you forget the shortcut, then you've got to look at a plus 1 multiplied by a plus 1 and do a binomial expansion. Take 3, and we've got a squared plus 2a take 2. Right, so that means that when x is equal to a plus 1, then y is equal to a squared plus 2a take 2. All right, so that's function notation, which isn't the real focus of the lesson. We'll keep on coming back to that. What we're going to do now is review our known templates. Now, remember, the whole idea is that we're looking at it in a form of y is equal to a x minus h squared plus k, where a is that vertical dilation factor. So when a is greater than 1, then we know that it's going to be a stretch, so a vertical stretch. When A is between 0 and 1, then it's going to be a vertical compression, so it's going to get squashed. And when A is negative, we know it's going to be an inversion, or it's going to be mirrored in the x-axis. It's going to be flipped upside down. H is that horizontal translation. So that means that it's going to be shifted right when H is greater than 0, and will be shifted left when H is less than 0 or negative. And finally, K is vertical translation. So that means it's going to be shifting up and down. When K is greater than 0, it shifts up. And when K is less than 0, it shifts down. Okay, so again, that's really quick, but this is something we've done previously. So it is just a review. All right, so the shapes go with the functions that we know. So the first one is a parabola. So the template for parabola is y is equal to ax minus h squared plus k. The shape, our general shape is like that. Y equals x squared. And its critical points are the turning point, which is hk. Now, every single one of these, we will have to consider also x-intercepts and y-intercepts. So I'll just put this up the top. We go always x-intercept, y-intercept. With the parabola, we can also look at a line down the middle, and that is called an axis of symmetry, but it's not as necessary as the other thing. So axis of symmetry is always going to be an equation which is x is equal to h. Okay. The second one we should know is a cubic. Now the template for cubic is ax minus h cubed plus k. Our critical point is a point of inflection, and again that will be hk, and it will look like this snake shape. That's where our hk is. That's our critical point. Back at our parabola, there's our turning point, that hk. The third one we looked at was a hyperbola, and that's in the form y is equal to a over x minus h plus k. Our critical points are not actually critical points, they're asymptotes, so they're lines that we cannot cross, and they will be x is equal to h and y is equal to k. So when we look at this, if we've got our line y is equal to k, and we've got our line x is equal to h, our shape of the parabola is that it stays within those opposite quadrants. As it approaches h, it goes down to negative infinity. As it approaches negative infinity in the x, it approaches 0 or the k value and so on. All right, so again, that should be familiar. You should know that. And again, we're looking at finding x-intercepts, y-intercepts as well to help us sketch those. Now the final one is an inverse parabola, which we kind of break down to a square root function. So we would have looked at it in the form y is equal to a square root x minus h plus k. Now, as we know, that square root function is just an inverted parabola, so it's turned on its side, and we're taking 1/2 of it because we can only do the plus or minus at one time to keep it as a function. The critical point, I still call that a turning point, and it will be hk as well. So if we look at that as a sketch, you can see here's a turning point. It would continue there if we had the full function, but we only have the 1/2 function. This is our h and k, and that is a shape that follows. So we need to know those shapes. We need to know those basic templates. We need to remember we have to calculate x and y intercepts, but we also have to understand that each of them has their own specific critical point. Okay, so we'll sketch a couple just as practice. So we'll do a hyperbola and a parabola. So we'll start with y is equal to 2x take 1 squared take 8. Okay, so if we're going to sketch this, obviously we can see that's a parabola, so we know straight away that we've got our shape. We can look at the fact that the a value is positive, and we know it's upright, and we know that it's shifted 1 across to the right and 8 down. So the first thing we can say is that h is equal to 1, and k is equal to negative 8. Now that's really useful because that tells us that our turning point is at 1, negative 8. Remember, with the h value, we're always inverting it, so that's a negative. That'll be a positive because the rule is that it's negative h. Okay, so there's our turning point. We've got one critical point already. We'll also look at the y-intercept, and the y-intercept is when x is equal to 0. So if we sub that in, y is equal to 2. 0 take 1 squared, take 8. So 2 negative 1 squared is just 1, take 8, we end up with negative 6. So our y-intercept is 0, negative 6. So now we've got a second critical point for sketching. Now last ones is we're going to look at the x-intercepts. And the x-intercepts is when y is equal to 0. So we've got 0 is equal to 2, x take 1 squared, take 8. We can add our 8 across. We've got 8 is equal to 2, x take 1 squared. Obviously, the goal here is just to solve for x. So divide by 2, and we've got 4 is equal to x take 1 squared. To undo the square, we want to square root both sides. So remember, when we square root, we've got plus or minus. So square root of 4 plus or minus square root of 4 is equal to x take 1. We've got plus or minus 2 is equal to x take 1. And we end up with x is equal to 1 plus or minus 2. So this gives us two solutions. 1 plus 2, x is equal to 3. And 1 take 2, x is equal to negative 1. So our x-intercepts are 3, 0, and negative 1, 0. So there's our two final points. So we know what it looks like. We've got 4 critical points, and sketching should be nice and easy from here. All right, we'll just do a rough sketch. It doesn't have to be perfect. We've got negative 1, 0, and 3, 0. We've got negative 6, and then our turning point is at 1, negative 8. So from that, we should be able to draw a nice representation of our curve, nice and simple. So every type of function that we graph, we need to make sure we're doing these things. We're determining the critical points or the critical asymptotes, and we're then calculating x-intercepts, y-intercepts if that's possible. They won't always be possible, and sometimes we just have to sub in a value to get a point to finish our sketch. Right, we'll sketch one more. So we'll look at what we can see, hopefully, is a hyperbola. Now, as soon as we see that's a hyperbola, we should know the shape. We know what we've got asymptotes that we have to find, and we can start by saying h is equal to 1 and k is equal to 2. Once we've got those, we know that our asymptotes are pretty easy to determine. We've got x is equal to h, which is x is equal to 1, and y is equal to k, which is y is equal to 2. So when we go to sketch this, and we might do this usually as soon as you know the asymptotes, because it sets us up. We know that y is equal to 2, so we can put a dotted line there, and we know that that's a boundary, a limit line we cannot cross, and x is equal to 1, x is equal to 1, and that's our other boundary line. So it's going to exist in these quadrants. Now, really important, you'll notice that I wrote those equations there. You must do that. So that allows us to see the equations of those asymptotes within the sketch. Y-intercept is when x is equal to 0. So we've got y is equal to 2 over 0, take 1, plus 2. So 2 over negative 1 is negative 2, negative 2 plus 2, and we end up here with 0. Now I could, and I will, solve for my x-intercept, but I already know my x-intercept is going to be at 0, because 0, 0 here. So we've got 0 is equal to 2 over x take 1 plus 2. We'll subtract this 2. So negative 2 is equal to 2 over x take 1. We want to multiply the x take 1 off the denominator. So we've got negative 2x take 1 is equal to 2. We can divide by negative 2 here. So now we've got x take 1 is equal to negative 1. And when we add -1, we get x is equal to 0. So that was just so when you have to do one of these ones that we don't already know what the x-intercept is, you're able to kind of follow that process. So now we can kind of draw in what the line looks like. We know it approaches the asymptote on both sides, so we can draw that approaching the asymptote. And as long as it's close to mirrored in the other section, we don't have to sub in any other values. If you really wanted to, we could easily sub in 2. So if we wanted to find out another point, we could say f of 2, which means we're subbing 2 into the equation. So we've got 2 over 2 take 1 plus 2. So 2 take 1 is 1, 2 over 1 is 2, 2 plus 2 is 4. So a secondary point would be that we've got 2, 4. Now you can do that as many times as you like if you're unsure, if you're having trouble sketching it. All right. Now, I'm not going to show you all the functions because that would just take too long, but there's plenty of practice in the next exercise and there's full solutions for you to check. All right. The final thing is modeling to templates. So when we're modeling to templates, generally, we've got 2 scenarios. So I'll set up 2 examples. One is that we can just be given information. So let's say that we've got a parabola which has a turning point at 1, 2. And it passes through 2, 5. Okay, so we've got information there. We know it's a parabola, and we've got enough information to determine h and k, but also calculate a. So this will be to get h and k, and this will be to calculate a. Now, the other scenario is you can be given a graph, and you might have to take that information from the graph. So let's look at a cubic function, where we might say, okay, our point of inflection is at -2, -1, and it passes through, there's a y-intercept at y equals 1, right? So for each of these, we've got everything we need to know. Knowing the template is really important, and then it's just a matter of determining the parameters. So being a parabola, we know straight away that the template is y is equal to ax minus h squared plus k. Now we know that hk, which is the turning point, is equal to 1, 2. So straight away we can pull out that h is equal to 1 and k is equal to 2. So that's really important, and that allows us to jump straight into a point where there's only one unknown parameter. So y is equal to x take 1 squared plus 2. Now the important thing is that we have this extra piece of information. Now this extra piece of information gives us an x and a y value that are attached to each other. So when x is equal to 2, then y is equal to 5. If we put those in, we've got enough information to be able to determine a. So 5 is equal to a 2 take 1 squared plus 2. And now it's a matter of just going through and isolating for a to determine what it is. So we subtract 2 and we get 3. 2 take 1 is 1, so we've got 1 squared, and so we end up here with a is equal to 3. Once we've got all of that, we can state our equation, and it is simply that y is equal to 3x take 1 squared plus 2. So that's our goal with modeling, is to come up with the equation that fits the scenario that's been given. So if we were to graph that, we would get a turning point at 1, 2, and it will pass through that 2, 5. With the second one, we can see that it's a cubic, so our template is equal to a x take h cubed plus k. Our h and k values are going to be that critical point, the point of inflection, which means we've got -2, -1. So h is -2 and k is -1. Now when we put them back in, we've got y is equal to a x take -2 makes it x plus 2 cubed, and k -1. So you can see we've got that same scenario where we've got our base template and the only parameter that's unknown is a. So if we take this extra point, when x is equal to 0, y is equal to 1, and we put that in, so we've got 1 is equal to a 0 plus 2 cubed take 1. Our goal now is to solve for a. So we add 1, we've got 2. 2 cubed is 8, so we've got 8a. And when we divide by 8, we end up with a is equal to 1 on 4. 2 on 8, which is 1 on 4. So our final model here in this scenario is y is equal to 1/4 x plus 2 cubed take 1. Now again, if we were to graph that, we would see the same shape passing through the same points. And there's our model, there's our solution. Okay, so thank you for listening. There'll be plenty of practice in the attached exercise. You can see you got some sketching and then some modeling to do to be able to get to a point with these skills that you are fluent and confident. All right, thank you.